Hello, everyone, and welcome to today's webinar titled Powering Through the Fluctuations, Building Electrolyzer Systems that Thrive on Intermittent Renewable Energy, hosted by John Cockerill. We're delighted to have you join us. Throughout the webinar, we encourage you to share questions using the Q&A feature located at the bottom of the panel on your Zoom screen, or you can post them directly into the meeting chat. If you're experiencing any technical difficulties, please let us know in the chat, and a member of our team will do our best to assist you. Thank you for joining, and I will now hand over to Claire Burtin, Head of Strategy at John Cockerill.
Thank you, Ron. Hello, everyone, and welcome to this webinar. Ron, can you confirm you see my screen still?
Yep, can still see the screen.
Okay, good, perfect. So yeah, welcome to today's webinar. We are going to talk about one of the most crucial aspects of electrolyzers for a green hydrogen project, how to design your electrolyzer systems and your plants for seamless integration with renewable electricity. So I'm Claire Burtin. I'm head of strategy for John Cockerill Hydrogen. John Cockerill is a global leader in electrolyzer systems. We are electrolyzer manufacturer. We've been in the hydrogen sector for more than 30 years now. We've sold more than 1,000 systems, and we have 2 projects that are above 100 megawatts in operation today worldwide. Before we dive into the webinar, I would love to hear from you, and if you can just drop some of your thoughts on the chat and answer, this question. So, in your opinion, and depending on where you are in the value chain, what do you think is your biggest challenge when it comes to integrating electrolyzers with renewables? We're going to go through some points, but obviously, if you have questions, feel free to drop them on the chat, and we'll have about 15-20 minutes at the end of the webinar to address the questions, and I'll try to address as many of them as possible. So first, let's do a bit of definitions and terminology, and let's define intermittency and flexibility. So I'll just go quick on these ones. Intermittency is obviously the variability of power outputs from renewable energy sources. So basically, when you have solar and you don't have the sun anymore, then you have a drop in the electricity production from your solar panels. And this is this creates variability in power supply that will go into your system. So electrolyzer plant, for example. And when we are going to speak about flexibility, we talk about the ability of the electrolyzer system or your plant to operate under these intermittent conditions, meaning the ability of the system to follow variable loads.
I'm sorry, Claire. Sorry to interrupt. I think there's a bit of an issue with your sound.
Ah.
If you just try speak now, just check it's working.
Yeah, I see. Yeah, I think I have, let me check, but I think my connection is good. Can you hear me now?
Yeah, it sounds clearer now. Yeah. I'll drop off again.
I can switch off my video if needed.
Yeah, we'll see. See, it sounds okay now, but then I'll let you know if it cuts off, and then we can try the video.
Okay. Good. So now let's just take a step back and look at historically what's the when the intermittency topic came up. So as you may know, electrolyzers is a very old technology. Electrolyzers have been developed for more than 200 years now, and were initially used for rather small applications, military application. Then in the 1900s, they were used for producing, hydrogen for different type of chemicals. In the late 1960s, PEM technology was developed. The original technology was only alkaline. PEM technology were developed for addressing new needs such as mobility through PEM fuel cells. And then as the renewable energy were developed more and more. And as you can see in this graph, we see a surge in the development and adoption of wind and solar energy production, which then leads to new question about, okay, now we were operating electrolyzer on a stable load for producing different types of chemicals. now we have this resource of renewable energy, they are cheap, they are available. Can we plug that solar and wind energy directly to our electrolyzer systems? And this came up, I would say, in the past 5 to 10 years. So it's a rather new challenge and a new topic for the electrolyzer technology when you look at the overall timeline. So we split here the flexibility needs from different setups in 3 big groups, and I will go through the different groups. So first one is off-grid. So it's when you have your electrolyzer that's directly connected to renewable power. In that case, you have very high power variability, because then you have all the weather variations that are going to influence the output of energy you can get. This will have an impact, obviously, on the load of your electrolyzer. So this is just an example of a range. Obviously, it depends on your energy resource. And this will also impact, how many start and stop you will have on your systems, and also the system, the stress you put on your system because of all this cycling and fatigue phenomena that are going to appear. And then in another case, so that's the middle case, you can have a purchase power agreement with a renewable energy producer, but you're still connected to the grid. And in that case, you can still have access to some stable power at some times, or you can have a mix of different purchase agreements. So you have, for example, a mix of, I don't know, a solar power and wind power, which enables you to have a more stable power input. In that case, you have, better load, fewer number of start and stops, lower system stress, but you'll still have an output of hydrogen production that's fluctuating and following the power input if you don't have storage. And the latest case is the base load. So this is basically what you usually have. You had in the past, which is operating your electrolyzer on a stable power input that leads to low power variability, but a very high electrolyzer load factor, which means that you can use your electrolyzer most of the time to produce hydrogen. And you have fewer starts and stops. So basically, let's say 1 start and stop per month for example, for maintenance, which has an impact on the system stress, which is much higher than what you can have when you're operating on high power variability. Now we will go quickly through the different states, and I won't go into all details about that graph, but just to give you an idea of, an example of what a curve of operating your electrolyzer could look like. Just try to use the pointer. So let's say you start your day with an electrolyzer or system switched off, and you switch it on. So you have some startup time, obviously, to make it work. This is true for alkaline electrolyzers. For PEM, the startup time is much slower, but then it depends on, for alkaline, for example, depends on the system and on what type of technology you're using. Then you're going to ramp up your load up to the nominal load, which is basically the load at which you're going to operate your electrolyzer most of the time when you have power available. And in case you have a drop in power, you can turn down your stack. So you have also a ramp down rate, which, this curve is not a one-off. So it takes time to ramp it down to the minimum turn down, which is basically the minimum load at which you can operate your electrolyzer on a safely manner. And this is determined by, the system safety parameters and the parameters of your system operation. And I would just want to emphasize what's an important data as well is the operating range here in the middle, which is basically the range in which you can operate safely your electrolyzer. So it's from the minimum turn down up to, for example, here you can have an overcapacity of 110. So basically your operating range is between 10 to 110% of nominal load. And then you can have also, this is interesting just to show you an example of, you can have different strategy to have your system in a hot standby, which means that you're not using it to produce hydrogen, but you keep it hot to make it start faster. So here you have several start and stop handling, and the system stays hot during these phases, enabling, a shorter time startup time than a cold startup. We'll be diving into this later to explain more about the parameters. But now that we've seen, the general concept of flexibility, just want to emphasize the challenges that you can have for a flexible operation. And I just want to mention that the parameters we're talking about are not just for when you want to plug with renewable energy. Obviously, when you plug electrolyzers with renewable energy inputs, you have much more fluctuation and needs for a flexible system than when you're using the grid. But even when you're using the grid, you might want to switch off your system or to ramp down for example, for maintenance, for managing different type of operation, or even for cost optimization in your LCOH. So this could also be a challenge for your system, even if you're connected to the grid. And obviously, I mean, we mentioned that already, but when you connect it to renewable electricity, you have different parameters to take into account. But one of the biggest one is, how to predict the load you're going to have in terms of electricity input, so weather and environmental condition, electrical supply conditions. So you have a lot of challenges, and it's very difficult to design a project. But so the question could be how and why would you do that? Why would you use renewable electricity when you can have a stable grid power? So one of the reason is that you can use this renewable energy to your advantage. There are a certain number of subsidies available for hydrogen produced using renewable energy sources. I'll just take the example in Europe and in the US, for example, where you have the RFNBO and 45V. And basically, these are subsidies that are available if you're producing hydrogen in the same time frame as electricity production, renewable electricity production. You also have condition on the fact that your electricity production should be nearby your plant, and that should be built also recently. So this means that you can benefit, for example, in the US for up to $3 per kilo of subsidy, but you really need to have the production of electricity that is matching the production of hydrogen in almost real time, which means that then you have to find solution to adapt to these requirements by either, designing your project differently, making sure your electrolyzer system are fit for that type of use, maybe putting some storage either for electricity or for hydrogen at some point in your project. The other advantage and reason why you should use renewable energy, I mean, despite the fact that obviously it's to produce clean and green hydrogen, is that you can also use that and leverage this as a cost optimization strategy to drive down your levelized cost of hydrogen. And I'll just give two examples. So one example is that you can adapt your operational strategy. For example, if you're taking electricity input from the grid, you can use your electrolyzer to manage and balance the load on the grid and switch it on and produce hydrogen only when you have favorable electricity prices, spot prices. And for example, when prices are too high and you see it does not make sense to produce hydrogen anymore because it's too expensive, you can just switch your electrolyzer off. And so, you can follow, price signals. The other cost optimization is if you have a flexible electrolyzer system design, you can optimize your project sizing. For example, I know your customer is asking you to produce, let's say, 200 tons per day of hydrogen. So you are going to dimension your electrolyzer system to produce this amount of hydrogen, sorry. I'm turning off my screen. Sorry, we have audio problem. I hope this is going to be solved. Let me know if it's still not working. Okay, thanks, Gary. Okay, so design strategy. is when you want to optimize the design of your plants. And so as I was saying, you can, for example, in some cases, you might say, okay, I need to oversize my solar panel to make sure that I produce the right amount of hydrogen in the end. So if you have in mind all those parameters, you can really optimize and design the size of your plant and the size of your, solar plant or renewable energy plant, and the size of your electrolyzer plant at the right sizing to produce what you need to produce for either yourself or your end customer, and also optimizing your levelized cost of hydrogen. So now, as I mentioned, this is not just about electrolyzer, this is about designing your whole project. And you have to take into account all those parameters in order to find the right design for your project. So we obviously are going to dive in about the electrolyzer parameters and all that, but I want to, while we go through that, I want you to keep in mind that what's important is your overall plant, and it's what are your requirements in terms of hydrogen production, and what are your requirements or your let's say your framework in terms of what you have as an input for renewable energy. So let's dive into the electrolyzers. So for looking at flexibility for electrolyzer, we consider those 5 factors that are super important. So first factor is the ramp up and ramp down rate, which is basically the rate at which your system can vary your output and can go from, let's say, 10% load to 15% load or 80% load. And then you have the operating range. So as I mentioned in the introduction, this is the range at which your system can safely operate. And this includes, consideration at stack level, but also at system level, not just for the stack. Then you have operating modes, which are, considering all the different modes of your electrolyzer. So for example, one system can have a very long startup time, which might be a problem if you want to do several switch on and off very quickly. Then you have degradation rate. So the degradation rate is not a parameter that characterizes the intermittency capabilities of a system. But we have found that, and it's documented in studies as well, that operation with frequent on and off cycles and load variation is affecting and impacting the efficiency of the system through increased degradation. So we think it's important to track that parameter as well when you benchmark systems for in consideration for your project. And last point is the tools for planning and monitoring. So this includes, tools to monitoring performance, system control, but most important for our topic here is a tool for optimizing intermittent operation, having support to make decision on stack management. Okay, we need to avoid videos. I'll try to go fast on the video one. So now, so here is the data we have at the moment, gathered from different companies on the different capabilities of different stacks. So as you can see, today PEM have a wider operating range at stack level. So here we're just at the level of one stack, than alkaline atmospheric and alkaline pressurized, which is in the range of like 30-40% to 100, while PEM can go down to as low as 5% or so at stack level. Then the percentage, the ramp up per second, again, PEM is very fast for ramp up, which means that they can go very fast from a load of 0% to 100%. They can ramp up in a few seconds. For alkaline pressurized, the technology is at around 4%. Which is not as good as PEM, but can still ramp up in a few seconds from 0 to 100. And in the contrary, alkaline atmospheric is much slower, and it takes more in the range of minutes to ramp up. And then you have the degradation rate in percentage per year. So Here you can see PEM, and that's recent documentation, and obviously everyone's working to improve their technology, so it might change in a few months or so. But today, PEM is reportedly to have higher degradation rates than alkaline pressurized and alkaline atmospheric when in operation with fluctuation. So now, this is the data at stack level. And again, I want you to really consider what are your needs for your project. When you're buying a car, obviously you want to, you want the Ferrari because it goes faster and it looks better. But if you're buying a car just to go and pick your kids up at school, maybe you don't need the Ferrari. Maybe you need a car with a large trunk, so you have a space to put all the school gears of your children in the trunk. So that's the same. Sorry for the comparison, but that's the same for electrolyzers project. Basically, the question to ask yourself is, okay, look, I'm looking at my load profile, and I'm going to ask myself, do I really need to have 10% per second ramp up, or maybe 0.3 or 4% is enough? And it's going to depend, case by case on each project. So that's why you really need to take into account and consider your hydrogen demand profile and your renewable energy profile. That's the first input you need to have. You need to really know, how much energy you're going to get from the grid or from your renewable energy source. And you should define that at plant level, and I will give you the example for, to illustrate why you need to do that at plant level. So here is a very simple example where we have stacks. We have stacks that can go down as low as 40% each. Okay. In one case, so we have 5 electrolyzers of 5 megawatts. They can go down at 40% capacity. So in the first case, you're like, okay, I have 5 stacks. I just ramp them down all to 40%. So your plant turn down is 40%. And if, for example, someone asks you to go as low as 8%, because this is what your solar profile looks like, you won't be able to manage that. And in the second case, it's the exact same stacks, exact same electrolyzer, but you don't manage the load the same way. And basically you say, okay, I'm going to switch off 4 stacks and I'm going to say just one up, which means one is operating at 40% and the other one are switched off. And then you're at 2 megawatt, which is basically 8% of 25 megawatt, and you meet the requirements for the plant. So just this to illustrate that you really, okay, you need to get the parameters of electrolyzer stacks, electrolyzer system individually, but then when you make your assessment, you have to make your assessment considering what are your requirements for the full plant and what are your options for operation management in reality. And this does not stop at just the stack. So your whole system configuration is going to be impacted by that. So this is the example for the other variables, because maybe it's not the stack that is going to be the bottleneck in terms of how low you can go and in your turn down, but maybe it's your gas separation unit, or maybe it's your power conversion unit. So just to give you this example, here we have a system with 4 stacks, 1 gas separation unit, and 2 PCUs. In the first example, we have a PCU. So in the both examples, we have PCUs powering 2 stacks at the same time. In the first example, we have the PCU being the limiting equipment, which means that it cannot operate with one of the stacks switched off. Which means that when you want to look at your turn down at plant level, you're going to have to switch off 2 stacks at the same time, because you're going to switch the full PCU line altogether. Which means that now your minimum turn down is going to be 4 megawatt, because you're going to ramp down the 2 remaining stacks to their minimum turn down of 40%. In the second example, you have the PCU that now has a configuration in which they can operate with just 1 stack on, which means that you can have 3 stacks down and just 1 on at 40% of its load, and you can go down as low as 2 megawatt. So this is, and this is also a compromise in design of your plant and how you select your systems. Today, what we do in the electrolyzer industry is that systems tends to be more modularized, but also mutualized, which means that you try to have, for example, one gas separation unit for more than just one stack. We have at John Cockerill systems with gas separation unit with 4 stacks. But if you do that, you need to make sure that you still keep some flexibility in the way you operate the stacks together. Last but not least is your system sizing and the storage and storage both for hydrogen but also for electricity. And so I'll go quick on this one because it's an animation and you won't hear what I'm saying. But basically, the point here is that you really need to assess all the different elements and all the bricks of your project together in the light of your levelized cost of hydrogen to make sure that the design you select is optimized both in terms of what you need for your operation, but also what you need for cost. This is the example that I wanted to show you regarding the system sizing and how you dimension the different systems. So as we've seen, you have some stacks that have not as good turn down as, for example, PEM, and the unit turn down, the individual unit turn down is maybe 40%. So this value is super important when you have small projects. When you have just one stack, if your turn down is 50%, then your plant turn down is 50%. But this graph shows that the more you add stacks, the less the minimum turn down of individual stacks matters if you can switch off individual units, which means that, okay, your individual unit, and here it could be, even your gas separation unit is the same. So if your unit goes down to 50%, but then you have 10 units, you can go down at plant level at around 5%. And you see here that, okay, when you have a low number of stacks, it really matters the turn down, but when you are planning for larger plants, it doesn't really matter as long as you manage all the operating parameters and being able to switch on and off the different elements independently. Okay, and when you've done that, so assessing really your needs, designing, fine-tuning your design with storage, with the right sizing, with the right assessments of what's your power input, then you also have to look at system controls. Why system controls are important? Because that helps you to make some decision on how to balance the load and how to distribute load between the different systems. So we developed an electrolyzer system control that enables to take as an input, let's say an order in terms of how many megawatts are available for production. And then the electrolyzer system control is dispatching the different load to the different systems. So for example, here I have you can have an energy management system that helps you determine how many megawatts you have available for production. So let's say this energy management system takes into account the electricity price, the renewable forecast with the weather, CO2 level of, for example, of the grid. If you have a demand on CO2 level and your hydrogen demand, they mix all these data together and they tell you, okay, for the next 4 hours, you have 12 megawatts available for production. And then you need to decide which stacks are going to be on, which stacks are going to be off. And this decision is complex for different reasons. So first of all, you have a lot of stacks and you can adopt different strategies. You can either optimize on cost. You also can optimize on degradation on your system, which means that you can try to limit the number of start and stop and fluctuation for some stacks. And I think that's it. You can optimize on degradation, optimize on cost, And I think that's it, yeah. And then the system allocates the megawatt amount per stack and helps you make these decisions directly. So this will help you to have, optimize and reduce your LCOH, basically limit stack degradation, but you can also run a theoretical simulation. For example, if you want to do a maintenance operation, you can define what's going to be the best operating configuration for your plant if you want to switch this and this stack for maintenance. And just to conclude, so it all comes down to the LCOH calculation. We've published a white paper on LCOH, and we had a previous webinar on that topic. So if you're interested in, you can look into our website. LCOH calculation is complex. You have to take into account a lot of parameters, and when you're considering flexibility, as we've just seen, it's even more complex. But you have options and strategy to optimize that, and we can help you to define what's the best configuration based on our products, and we know how our electrolyzers are going to operate, what they can do, they cannot do. So we can help you to fine-tune your design at plant level with the information from our systems. And then, I think one of the questions, and that is very often asked to electrolyzer manufacturer, and especially alkaline, is, okay, can your stack really operate using intermittent operation? So as you've seen in the electrolyzer details of the parameters, alkaline are not as good as PEM in terms of individual stack performance. But then at system level, if your system is well configured, you can totally manage the load, manage the variability load the same way as PEM would do. And so this is an example of power input profile with electrolyzers and with the parameters of our own electrolyzer that we did through a simulation of hydrogen, what hydrogen production would look like when you use 60 of our electrolyzer to power this plant. And this is what it looks like in terms of, okay, when you need to switch on and off electrolyzer, and that's basically what's behind our electrolyzer system control is, okay, we need to manage which one are going to switch on, which other ones are going to be switched off. If you know that you need, I don't know, it's just an example. If you know that you need 1 hour to switch one on, you need to maybe heat it up before, so you have different strategy on managing these aspects of starting them on and off. Yes, this is basically the proof that this is possible as long as you design well your project and you know well your initial load. And last point is that I just want to mention that John Cockerill has created a joint venture called Rely, and partner with Technip Energy on that joint venture, and Rely is proposing solution at plant level. And can help you also to optimize efficiency, balance of plant, and do some simulation at plant level for the best configuration for your plant. So after this long presentation, key takeaways from that presentation. So first, you have to keep in mind that intermittency is a relatively new challenge, which means that this is not just for John Cockerill, this is for everyone else. We have very, very limited field experience on operating system under intermittent conditions. So we are running systems already. Most of the systems that are in operation worldwide today are running on stable power. So we are working on getting data and information about how systems are behaving under intermittent conditions, but this is, let's say, still the beginning in the sense that it's not been done for 40 years. It's just been done in the past few years. Second point is you need to focus on the key technology variables and make sure that you focus on the right parameters that are going to be critical for dimensioning your project. Third point is you need to keep your plant level goals in your mind at each steps. which means that you need to keep in mind that you're not looking at individual stacks, but you're looking at optimizing a whole plant. And to optimize a whole plant, you have a lot of parameters, you have a lot of levers, you have a lot of options, and you need to know what you want to optimize and how you're going to do that and what solutions are available for you to do that. Fourth point is, okay, using tools to optimize at plant level design. So this can be tools, like the electrolyzer system control, but you can also use tools to model different options and look into the LCOH and see what's going to optimize your LCOH. And the last point is obviously choosing the right technology for the full lifetime of your project, taking into consideration your needs and what's available in terms of technology on the market today. And finally, we've recently published a white paper on this topic. This is much more detailed than what I've just presented here. So feel free to download and happy to hear about your inputs and your feedback on that paper. And I think I'm done. Let me put up the chat to look at your questions.
So we've got some questions in the Q&A tab as well, Claire. And some people have moved theirs from the chat into there, so it might be easier for you to follow them.
So you it's better to follow on the Q&A. Yeah, okay.
Yeah. Have you got access to it?
Yeah, I've got access to it. So what dictates the minimum load of an electrolyzer? So basically, the minimum load is defined by safety. So what's behind that? Basically, when you turn down, and again, apologies because I'm not a technical expert. So this is going to stay rather high level, but basically when you turn down electrolyzer, you have hydrogen to oxygen and oxygen to hydrogen phenomenon, which means that you have some molecules of hydrogen that are going to cross and go on the other side of the cell. Then this is creating a mixture of hydrogen and oxygen that can be flammable, which may lead to explosion at some point. So basically, the flammability range of hydrogen in oxygen is between 4% to 95%, which means that when you have a mixture that goes with hydrogen at more than 4% in the mixture, it's going to be flammable. So basically what's going on is that you don't want to go to that level. And so basically today the systems are designed to safely operate and to go much higher than that. So basically it's like 1.5, 1.8, the limit at which the system is going to just switch off for safety. And so that's why you won't be able to operate below that point. And so there are different sort of strategies to work on that minimum load. If you want to push back this minimum turndown and the moment where you're going to have this mixture of hydrogen H2O that's going to be too high, one of the option is to increase the current density. But this means that you're going to degrade your efficiency. And this also means that you will need to have higher quality materials within your stack, which means that this is going to be more expensive. So basically, you have, it's always about trade-offs. So you're going to have to decide if it's really worth it having, a turndown of 20%, but the stack that's, 15% much more expensive than initially. And basically that's, towards where the different R&Ds are going. So, for example, Chinese players are much more in favor of keeping this turndown to 30-40%, because they consider that what's more important is to have an electrolyzer that's cheap, and they can manage the load in a different way. And then there are other players like ThyssenKrupp, for example, and Verdagy. They are working on finding different options for improving the materials and increasing the current density. So it's a two-way strategy, but basically this is the story. Let me look at the other questions. So I have a question on so there are questions. I'm just trying to filter which one are going more often. So between so just quick question I can answer. More stacks allow greater turn down, but how does unit capex behave with more stacks? So basically, I mean, price stack is not going to change, but the capex usually when you have, and that's again the question of mutualization. If you have just one gas separation unit for 4 stacks, for example, it's going to be much cheaper than having separate gas separation units. So in terms of capex, you are going to gain, but obviously, if you don't need those stacks, you're not going to add more stacks just to get better turn down. And so then there is a question about degradation of membranes and electrodes. So I won't be able to tell you which one is more affected because it's a very technical question. But the degradation, and again, the degradation, it's not just about electrodes and membranes. So I just want to emphasize that the fluctuations in the load is also affecting the other parts of the systems because of, for example, changes in pressure. This can affect the sealing, the pipings. When you switch on and off, it's going to create fatigue not only for membranes and electrodes, but for the other parts of the system as well. So this has to be considered in an overall system, and not just about membranes and electrodes. But obviously, membranes and electrodes are the core of the stacks. So they are, and they are the core of performance. So if you degrade the membrane, the degradation impact on the efficiency is direct. So question about the 4-stack 25 megawatt example is not based on IOF wind project. It was just an example to give you some numbers. So there is a question on John Cockerill development. So John Cockerill developed regarding the control system. We developed the electrolyzer control system, which is basically very linked to our stack and the knowledge we have about the behavior of our stack that we are now able to model based on return on experience we have from stacks in operation. And the energy management system is something that, yes, it's developed with Relay as well for the Clear 100 product, which is basically an offering of a 100 megawatt plant that's optimized for large scale projects. So again, there are a lot of questions about degradation. So So degradation is a very complex phenomenon. So the way we are monitoring that is twofold. So first, we have data coming from the project that are already in operation with our stacks, and through that we get a lot of very useful information on how to improve and adapt the next generation of the stacks to degrade less under intermittent operation. That's one thing. And the second thing is that we also have test benches to that are running and that are let's say mimicking degradation cycles. So it's the same as when you cycle for other technologies. So you do a lot of start and stop to kind of like accelerate degradation and understand what are the parameters that are affecting the degradation within your stack, and how you can what kind of solution to mitigate this degradation you can put in place. So this is but again, this is not let's say a perfect science, and it's really dependent on each system. So basically, what's your electrode membrane structure? Do you have any systems to let's say diminish the impact of the on-off cycles on your system? And this is not something that this is not a number. Let's say saying that that's okay on a normal operation it's 1%, on degradation under these parameters is this percent. We have let's say cases based on the data we gathered on projects for which we can say, okay, if you start and stop for this time, you might have a degradation of this amount, but this is not at this point something that's a science that's, let's say, true for all electrolyzer system, and they behave the same way from all suppliers, let's say it that way. Yeah, so again, there is a question about the load at the system level and then the degradation at the system level. So obviously the degradation comes both at system level and at stack level. So you have the degradation of the stack, and this depends on how you're going to make the load in the stack fluctuate and how many starts and stops you're going to do. And then you also have the degradation on the system. That's what I mentioned about, for example, the gaskets or the pipings that are going to also experience, stress for all these cyclings. So a question about the plan. So for now, John Cockerill has only pressurized alkaline technology, because we consider that alkaline technology is the one that's the best suited for the needs of large-scale projects at the lowest levelized cost of hydrogen, and that's the technology that has been widely developed globally, and that's proven. So that's why we worked with this technology, and and as you've seen in the presentation of the stack parameters, pressurized alkaline has a faster ramp up than atmospheric alkaline. Plus you have an output that is pressurized, which gives you advantages in terms of the fact that you don't need any additional compressor. I mean, you need additional compressors, but you don't need to compress at very low pressure levels, and that gives you gain in capex. So we think that for now, pressurized alkaline is the best technology to address most of the projects, and that with the system controls and the clever design, you can address the needs as was shown in the model and simulation, you can address most of the needs of the project in terms of adapting to intermittent load. So we don't have, on the short term, design philosophy for hybrid system with PEM, because we don't manufacture PEM systems. But we do believe that, for markets like, as you mentioned, India and Middle East, we will still be able to manage intermittent load efficiently with our current systems. So I have a question about performances between Chinese and European stacks for John Cockerill. So we do have different product lines that have different characteristics in terms of performance, cost, but this is not Chinese and European stacks. So we just have two stack lines, S&P series, that are, on different structures, different internal parameters, and hence different cost and performance. So, question about the best form of storage and transportation of hydrogen. I think it's a bit of outside question from flexibility, but just want to mention that storage is super important when considering flexibility. And the main reason why, and I didn't touch this point in the webinar, is that what's important in the end is your hydrogen offtake. If you're developing a project, you have probably have a customer, or you are your own customer wanting to have a certain amount of hydrogen delivered. And when we're always talking about how electrolyzers can adapt to fluctuating inputs, but in the end, if you have a fluctuating input, then you have a fluctuating output of hydrogen production, which means that then the problem is pushed further along the chain. And if your off-taker wants to have a stable input of hydrogen, for example, to produce ammonia or to produce something for its chemical plant, some of these chemical processes can fluctuate, but some of them cannot. And so maybe their on turn down is max 50%. So you need to at least provide hydrogen for 50% at 50% load to them, which means that, I don't know, if your electrolyzer system can ramp down to 10% because of fluctuating electricity, you won't meet the need of your off-taker, and you will have to add hydrogen storage between your electrolyzer and your off-taker, or you will have to put a system after the renewable energy production, like either battery or other type of electrical storage, to store electrical energy, and then produce hydrogen in a stable output. And this question about whether you should store electricity or whether you should store hydrogen, or maybe both, and in what would be the size of both system, really depends on LCOH and on also the capabilities you have around your plant. So some projects, they have salt caverns nearby. They aim at storing big amounts of hydrogen in those salt caverns for later use, or for transportation, or for even, for example, to store hydrogen for, let's say, answering the needs for fluctuation through seasonal renewable energy fluctuations. So if you have salt cavern nearby, then you can say, okay, I don't need to invest more to store electricity, before hydrogen production. I will just store hydrogen. But if you don't have that, and maybe you're looking at how much it costs to store hydrogen in your current setup, maybe it's more interesting for you to store just electricity instead of storing hydrogen. And then to answer your question, best form of storage and transportation of hydrogen. So there are several possibility, but I would say that it really depends on what's the quantity you want to store and transport, what's the distance on which you want to transport and store hydrogen. If you want to transport it from one city to another, it's different than if you want to transport it from Canada to Germany. You won't use the same solution, and it won't have the same cost as well. So I would say the most popular forms for large scale global transportation is either ammonia, methanol, or liquid hydrogen, and liquid hydrogen being the third solution, not the first, not the pressurized hydrogen solution for long distances. So there is a question about slow start for gas production. So alkaline electrolyzer, they are using they need to be at a certain temperature to operate at their nominal value, which means that that's why we distinguish cold startup and hot startup. So if you start when the stack is cold, then you need to heat it up progressively, which could take some time to make it possible for it to produce hydrogen at the right efficiency and at a nominal load. Now, the different strategies that are in place for pressurized alkaline stack is investigating possibility to have a hot standby where you keep your stack hot because you're going to need to start it up shortly, and you want to gain some time. So this is one of the solutions that's today in place for increasing the, let's say, the reactivity of the stack, alkaline stack at startup. So again, battery energy storage, I think is it's at scale today, a solution that's at scale today, and that needs to be considered when you design your projects to see if batteries make sense to help limit the fluctuation of the energy supply. And again, it's not just to help limit the fluctuation, it's to help you improve your LCOH. So if it's more interesting financially to put BESS, I would definitely recommend putting BESS rather than keeping the fluctuation and decreasing your LCOH. So we don't have a calculation for the degradation of PEM or AEM because we're not producing these technologies. So I would recommend you to contact PEM and AEM suppliers to understand how they calculate degradation for their stacks and what kind of testing they are doing for degradation. So in the field, the lifetime of stacks, that's a good question. So we, as I mentioned in the introduction, we have we've been delivering systems for more than 30 years. So we have systems that have been operating in Asia for several years now. So, but again, yeah. So we have some experience on the stack lifetime in that matter. So John Cockerill does its own R&D for electrolyzers, yes. So we do have a R&D team, we have R&D facilities. We also partner with universities in Europe and abroad on different R&D projects, both short-term and long-term projects R&D. So the question about PEM and alkaline, so there is a question whether when PEM will be more suitable than alkaline. So it's not that PEM is less suitable than alkaline at the moment. It's that PEM has less return on experience on large-scale projects. So for now, and I don't have the numbers because it's evolving very fast, but the alkaline technology has much more experience because most of the projects in operation worldwide are using alkaline technology. So there is a lot of information on real field experience than PEM at scale. I mean, so scale means several several dozens of megawatts and even more than 100 megawatts. And for PEM, I think they commission a plant that's more than 100 megawatt, but for many years the largest PEM plant was 20 megawatts. So it's still lower than what you can see for alkaline today in terms of return on experience. So PEM is not worse than alkaline, just a different type of technology with different level of maturity.
I think we have time for maybe one more question, Claire.
Okay. So we have estimates. Do we have estimates of range for total install costs for one of our electrolyzer system for typical project size? So I would invite you to just ask our commercial team if you have a specific project in mind, and they will come back to you shortly.
Okay, brilliant. Well, thank you so much for your time, Claire. I really appreciate you being here, and hopefully everyone's enjoyed the presentation as well. So yeah, I just want to, as well as thanking Claire, I want to thank you all for joining today. I hope you've enjoyed the webinar. Recordings will be made available next week. So yeah, have a great rest of your day, and we hope to see you at the next virtual session.
Thank you, Ron, and thank you all for your questions. Have a good afternoon. Bye.
Bye, everyone.